All right, we're going to go through chapter 15 homework, and then we will go to some more chapter 16. All right, the first homework problem, chapter 15, I believe, is 15.36. All right. So for each following reaction, label each as an acid base, indicate which are conjugates. All right, so we have H2PO4 minus added to HCO3 minus, and that goes to HPO4 minus 2 and H2CO3. All right, so the conjugates are easy to point out. These are your conjugates. They differ by 1H plus, and so these are the conjugates. So easiest way to do this one is to look at your conjugates, and then obviously the one with more H's is your acid. And so here is the acid with its conjugate base, because there's two H's versus one H. Same over here. This one has two H's, this has one H. So this is your acid and the conjugate base. All right, and so you have labeled your conjugates, acids, and bases. All right, so that was part A. Part B was your F minus plus HSO4 minus. All right, so this one you can actually predict what's going to happen. Up here, you couldn't predict because both of these both started with H's, so they both had the potential to be the acid. Here, you only have this one with the H. It is the only one that has the potential to be the acid. All right, and so it's going to donate its hydrogen to the F, and you're going to get HF, and then you're going to get your SO4 minus 2. So your F minus has it's the base with HF, its conjugate acid. They are conjugates. They differ by 1H plus. And again, the one that has more H's than the other one, that is, of course, the acid. And these are conjugates because they differ by 1H plus. And here is the base. Part C, HSO4 minus plus H2O. Again, here this one could go either way, so you couldn't predict it. They have to give you the products in this one. SO4 minus 2 and H3O plus. So once you have them, you can easily line up the conjugates. They differ by 1H plus. The one with the one extra H, that is your acid. The one with one fewer H is your base. Again, easy to detect. The ones that differ by 1H plus, they are your conjugates. The one that has the extra H is the acid. The one that has one less H is the base. And so there are your acid-base conjugate pairs labeled. And then finally, part D, you have H2S plus Cn minus. So this can only go one way. Okay, you're going to get your HS minus and your HCN. So again, easy to see which two things differ by 1H plus. Those are your conjugates. The one that has the more H's in your conjugate system, that's your acid. It has one more H than your base. Your acid has one more H than your base. And so there are the conjugate acid-base pairs labeled. All right, so that was 1536. That should be quite easy to do. All right, 1540. 1540, this one usually will catch people off guard because there are not many Lewis acid, Lewis base questions. All right, so InCl3, when we write the Lewis structure of InCl3, all right, so you have your Cl, which has 7 electrons from the periodic table. All right, so it comes in with 7 electrons. Your In comes in with 3 valence electrons. All right, and so here is your Lewis structure. All right, and so when you react that with another Cl minus, what happens is an electron pair will connect to your In. And so you now have In connected to 4 Cls. All your Cls have 7 electrons, just like they're supposed to, but now the In has 4 electrons. And so your formal charge of your In is a minus charge. All right, and so we see that the Cl minus is an electron pair donor. It donated the electron pair to the In. We see that the In is an electron pair acceptor. And so you have to know those definitions. If you're an electron pair donor, you're a Lewis base. If you're an electron pair acceptor, you're a Lewis acid. Lewis acid is an electrophile, which means it would love to get electrons. And your Lewis base is a nucleophile. It is looking for a nucleus to give its electrons to. So you have a nucleophile and you have your electrophile. All right, but we call them, when you're doing, they're called both. So if you have a Lewis acid, you have an electrophile. If you have a Lewis base, you have a nucleophile. All right, but we are going to most likely just stick with the Lewis acid, Lewis base system, but you should know an electrophile is something that would love to get electrons. That is a Lewis acid. All right, nucleophiles looking to attack something, and that is your Lewis base. All right, so that was part A. Part B is exactly the same as part A. They could have changed it up a little bit, but it's exactly the same. B, Br3. So again, B has 3 valence electrons. Bromine has 7. All right, so your B with your Br3, it looks exactly the same. The bromine brought in its 7. Your boron brought in its 3. All right, and so when you react that with your Br minus, this electron pair will go to the boron, and so you now have a boron with 4 bromines attached. And the Br should have had 3 electrons, and you see that it has 4 electrons around it. The B is the minus, boron is the minus. Bromine should all have 7, they all do. All right, so you see that this was the electron pair donor. It donated the electrons to the boron, and so that is your Lewis base. And you see that the boron accepted the electron pair, so the electron pair acceptor is your Lewis acid. All right, so you have to know what a Lewis acid and a Lewis base is. Lewis base, electron pair donor. Lewis acid, electron pair acceptor. That is 1540. All right, next one. 1552. Order each of the following pairs by acid strength, giving the weaker acid first. All right, so here we have HNO3 and HNO2. Well, this one's very simple. This is one of your 6 memorized strong acid, and this is a weak acid. And so if they want you to put it in order of weak acid to strong acid, well, you write HNO2 first, and then you write HNO3, because one is a strong acid, one is a weak acid. That was part A. Part B, the question is HCO3 minus and H2CO3. Well, these are conjugates. And of course, the acid is the one with the most H's, and then the base is the one with the one fewer H. All right, and so that one's listed. All right, so if this is a base, it's definitely a weaker acid than the acid. And so your HCO3 minus is a weaker base, and H2CO3 is a stronger base, because HCO3 minus is actually a base, not an acid at all. All right, so in part C, we have H2S and H2TE. All right, so this would be helpful to have a periodic table. And let's try the flipped periodic table. No, not the flipped. Okay. So if we scroll down and look sideways, we can see, or if you have your own periodic table, you have S is below O, and then TE is below that. The further you go down, the more acidic you're going to be. So you need to know your trends for further down the periodic table, the more acidic you're going to be. So the less acidic is your H2S. The more acidic is your H2TE. All right, so H2S is an acid, and if you go up one, you have H2O, which is neutral. So again, as you go down, you get more acidic. As the atom attached to the hydrogen gets larger, the more acidic that compound will be. Part D, those are nice and simple. When you have one that is a strong acid and one that is not, that is an easy thing. So HCl, that's a memorized strong acid. This is not a memorized strong acid, which makes it a weak acid. And so you have your H2S and you have your HCl. The weaker listed first. So you always like it when one is a memorized strong acid, then the other one is going to be weaker. All right, and then the last one is the same rule as a previous rule, where we have our H3PO4 and our H3ASO4, which is not the same rule. All right, so this one is very interesting, because this is different than when we had the one above. So the one above here was the H is attached to the S, the H is attached to the TE, and when the H is attached to something larger, it is a more acidic compound. All right, and so your H2TE was more acidic. When you have an oxyacid, which means that you have oxygen and you have an acid, the H's are attached to the O. So when you write this out, you would have your OH, you would have your OH, you would have your OH. And same thing here, your AS, it would look exactly the same. OH, OH, OH. So this one is different because the H is attached to the exact same atom. All right, it's not a larger atom. It's not one that is more electronegativity. It's exactly the same atom. So then you go with the electronegativity. And so since P is more electronegative than your AS, then your the H3PO4 is a stronger acid. So the weaker is H3ASO4, and the stronger is your H3PO4. The analogy here, if you don't remember this one, you can go and do two that are much easier, but would have the exact same rule. We can look at HClO4 versus HBrO4. And so we already know the answer to this one because this is a memorized strong acid and this is not. All right. So again, this is an oxyacid. It has oxygen and it's an acid. This is oxygen. So they're both oxyacids. All right. And so both of those, the OH is the H is attached to the O. So it's the same atom, same size, same electronegativity. And so then it comes down to your electronegativity. And since chlorine is more electronegative than bromine, this is a stronger acid. And so the analogy for E, which is a very hard problem, is your strong acid HClO4 versus the weak acid HBrO4. And so this is not part of the question, but this is going to hopefully help you figure out the answer to part E. All right. So that was number 52, 56. Solution is 0.03 molar HNO3. All right, so HNO3 is a memorized strong acid. All right, and so when you have a strong acid, HNO3, that means that it goes completely 100% ionizes to H plus and NO3 minus. So if you want to do initial and you have 0.030, 0, and 0, all right, there is no equilibrium here. It goes to final because it is 100% ionized. Final, this is 0. All right, there's no equilibrium here, not an equilibrium arrow. When you have a strong acid, 100% goes to the right, and you do have zeros. It's not an equilibrium. And so this is 0.030, this is 0.030. And so in 56, it says you have a 0.030 molar HNO3. What is the hydronium ion concentration? Well, there it is. It is 0.030 H plus. And H plus is the same as H3O plus. What is the hydroxide? Well, we know Kw is a constant. 1 times 10 to the minus 14, 0.0 times 10 to the minus 14, and that is my H plus concentration times my OH minus concentration. All right, so you simply have to take your Kw and divide by your H plus. So you take 1 times 10 to the minus 14, and divide that by 0.030, and you get 3.3 times 10 to the minus 13. So your OH minus concentration is 3.3 times 10 to the minus 13. So there's your OH minus concentration. Your H plus concentration is equal to 0.030 mole. And when you multiply those two numbers together, you get 1 times 10 to the minus 14. All right, so that was 56. 58. A saturated solution of magnesium hydroxide. Okay, so we have magnesium hydroxide. All right, and it has 3.2 times 10 to the minus 4 molar MgOH2. All right, so it is 3.2 times 10 to the minus 4. right, what are the hydronium ion and hydroxide ion in this solution? So we have a saturated solution, all right, which means that we dissolved as much as possible. And so the most that could dissolve was a 3.2 times 10 to the minus 4 molar of MgOH2. So when that dissolves, that goes into Mg plus 2 and 2OH minus. And so it all dissolved in this solution. And so this goes to 0, and this, all right, so this is minus x plus x, and here is the tricky part. It is the plus 2, the coefficient of 2x. All right, and so this is 3.2 times 10 to the minus 4. This is 6.4 times 10 to the minus 4. And so your concentration of OH minus is equal to 2x, which is equal to 6.4 times 10 to the minus 4 molar. And then it asks for the H plus concentration. So you know that your H plus concentration times your OH minus concentration equals the Kw, which is a constant 1.0 times 10 to the minus 14. So when you take your 1.0 times 10 to the minus 14 and divide by your concentration of OH minus of 6.4 times 10 to the minus 4, you get an H plus concentration of 1.6 times 10 to the minus 11. And if you wanted the pH of this, you simply take the negative log of that answer. So if I take the negative log of that answer, I get a pH of 10.81. It asked for the pH, but it could have 10.81. All right, so of course, magnesium hydroxide is a base, so you stick that in water and your pH is going to be above 7. All right, so here is a stoichiometry. It is a make sure you have that is not just X, that is 2X. There are 2 OH minuses in MgOH2. All right, but it only asks for the hydronium ion. That's the H3O plus, which is the same as the H plus, and the hydroxide ion. I just threw in the pH because many times pH is asked for as well. All right, the next one in chapter 5 is 1574. Solution of lye. Lye is sodium hydroxide. It has a hydroxide concentration of 0.050 molar. What is the pH? All right, so we did this one a different way. We're going to do it a different way this time. All right, so this time, instead of using the H plus and the OH minus equaling Kw, which you can do, we already did it that way, I'm going to go to my POH. And so the POH is equal to the negative log of your OH minus concentration. So I'm going to take the negative log of 0.05, and I get a POH of 1.30. So my POH is equal to 1.30. And I also know that my pH plus my POH is equal to 14. And so then I can get my pH, which is a 12.70. All right. It did not ask for pH, I don't think. Yes, it did. It did ask for pH. All right, great. And if you want the H plus concentration, you can simply plug that in and get your H plus concentration. Again, it is not asked for. But it could have been asked for. And that would be a 2.0 times 10 to the minus 13. But the question was, what is your pH? And that is 12.70. All right. I think this is the last one, 15.78. All right, morphine is a narcotic that is used to relieve pain. A solution of morphine has pH is 9.61 at 25 degrees Celsius. What is the hydroxide concentration? All right, so you can do it a number of ways. I'm going to go to the POH because I know that my pH plus my POH is equal to 14. So that is a 4.39. I add those two up, I get 14. And so my OH minus concentration, I know that's equal to the negative log of my concentration of OH minus. So I take the negative of both sides, that gives me a negative 4.39. Then I take my anti-log, my inverse log, which is a 10 to the x button. And so that is 10 to the negative 4.39. And my OH minus concentration is 4.1 times 10 to the minus 5. All right, and if I wanted to get my H plus concentration, you could do that from the pH, or you can do it from your OH times your H plus gives you your KW. Either way, you're going to get hopefully either way, you get a 2.5. It's a 2.45, so that one could go either way, times 10 to the minus 10 molar. So if we did 1 times 10 to the minus 14, divide that by 4.1, so yeah, so if you do it a different way, you might get a 2.4 instead of a 2.5. Again, if you carry out all the numbers, it would be a 2.5 if you round it and do it a different way. So again, if you're off by a number here or there, chances are you're doing it right. You're just rounding numbers. I don't round until the very end. All right, so that is the end of chapter 15 questions. So now we're going to go and do some chapter 16 questions. All right, so I'm going to start with number 1680, well, 1578, and that goes to 1680. All right, so we're going to do problem 16.80. All right, it says, what is the pH of a buffer? So we have a buffer. Anytime you see the word buffer, first thing you should think of is the pH is equal to the pKa plus the log of A minus over HA. So when it says you have a buffer, that is the equation that you should be using. All right, and it says that we have 0.1 molar of propionic acid, which I will just label as HA, and 0.2 molar of sodium propanoate, which is A minus. And so I look up propionic acid and I get the Ka. So the Ka of the propionic acid out of table 16.1, I think it is 1.3 times 10 to the minus 5. All right, and so then I just have to get my pKa, which is the negative log of my Ka. So I put in negative log of 1.3 times 10 to the minus 5, and I get a pKa of 4.89. All right, so that's my pKa. So now I just put it into my buffer equation. My pH is equal to the 4.89, the pKa, plus the log of my A minus concentration, which is 0.2, over the concentration of my HA, which is 0.1. And so, plus log And I get my final answer for the pH to be 5.19. All right, and so this would be a good buffer. It says it's a buffer. It's going to be a good buffer at whatever your pKa comes out to be. So this would be a great buffer if you wanted something to stay close to 4.89. All right, so you want your buffer pH to be very close. You want your pKa, that's what you're looking for. If you needed something that needed to stay at a pH of 4.89, then this buffer system using propionic acid and propanoate would be a great buffer system. All right, 1682. What is the pH of a buffer? Again, it says the word buffer. You're right. pH is equal to pKa plus log A minus over HA. What is pH of buffer solution? That is 0.15 molar of methylamine and 0.2 molar of methyl ammonium chloride. All right, so when you see this, you need to think NH3, which is ammonia, and NH4 plus, which is ammonium. All right, and so when you think of this, this is your A minus, this is your HA. All right, so when I see that I have a methylamine 0.15, so I know that this is the 0.15 molar. And then I have my methyl ammonium chloride of 0.2. I know this is my 0.20 molar. All right, so when you have ammonium, that's you're going to have your ammonia, ammonium versus then your ammonia. So you need to know that your bases, many of your bases have a nitrogen, and then its conjugate acid is going to have an extra H and a plus charge normally, just like you have your ammonia and ammonium system. So you have to be able to recognize which one is your acid and which one is your base. So it's a very easy question if you can do that. In 82, there is no Ka for our methylamine, but we have a Kb for the methylamine. So we have our Kb. So the methylammonium chloride is not in the chart, but we do have our methylamine in the chart. Kb is 4.4 times 10 to the minus 4. But since our pH is equal to pKa plus the log of A minus over HA, we have to remember that a Ka times a Kb is equal to the Kw, which is 1 times 10 to the minus 14. And so we take our Kw and divide by the Kb. So you take 1 times 10 to the minus 14, divide by the 4.4 times 10 to the minus 4, and you get a Ka value of 2.3 times 10 to the minus 11. All right, but actually we don't want the Ka, we want the pKa. So we need to take the negative log of this value. So the negative log of this answer is 10.64. So now we have our pKa of 10.64. All right, and so now to get the pH, that's equal to the pKa, 10.64, plus the log of your A minus. The A minus is the 0.15, divided by the HA, which is a 0.20. And that gives you a 10.52. All right, so since you had a little bit more of your acid than you did of your base, your pH comes down slightly from the 10.64. So again, if you're looking for a buffer that's going to keep your pH close to 10.64, then this would be a great buffer system. That was 1682, 1684. How many moles? All right, so this one gets a little confusing because I always work in molarity. So note that they are asking for moles here, not molarity. How many moles of HF? Not the molarity of HF. Must be added to 250 mils. 0.25 molar sodium fluoride. All right, sodium is always a spectator ion. I always get rid of it. This is my F minus here to give a buffer of pH 3.50. Ignore the volume change due to the addition of hydrofluoric acid. The Ka value for hydrofluoric acid is 6.8 times 10 to the minus 4. All right, so again, how many moles must be added to this to give a buffer? So it says that we have a buffer, and so pH is equal to pKa plus the log of A minus over HA. All right, so we have the pH that we need. We want the pH to be 3.5. We can find the pKa because we have the Ka. So to find the pKa, we take the negative log of the 6.8 times 10 to the minus 4, and we get a 3.17. So that's equal to 3.17 plus the log of A minus. All right, well, it says that we have a concentration of A minus of 0.25 molar over HA, and in this case, that is our HF. But note, when we solve this, we are not getting the answer because we are getting this in terms of molarity. So we would know the molarity of our HF. All right, but how do we solve this mathematical equation? All right, well, the first thing we have to do is subtract 3.17 from both sides. So we have a 0.33 is equal to the log of 0.25 divided by HF. All right, so then we have to take our inverse log on both sides. All right, so you have your inverse log, your anti-log, which is your 10 to the x button on both sides. So 10 to the 0.33, 10 to the log 10, that just gets rid of that. And you have 2.14 is equal to 0.25 divided by your concentration of HF. All right, so now we have to solve for HF. So the concentration of HF is equal to, so we multiply both sides by HF, multiply both sides by HF, and then divide both sides by 2.14. So it is 0.25 divided by 2.14. And that is a 0.12 molar. To more sig figs, it is a 0.1169. All right, so that is the molarity that we need for our HF. All right, but it didn't say what molarity do we need. It said how many moles, and it also said that we have 250 milliliters. And so this is a 0.1169 moles HF per liter of solution. That is your units for molarity. And it said that we had 250 mils. And so that is a 0.250 liters of solution. And so we have to multiply this by 0.25, and the answer to sig figs are they given? 2 sig figs, 0.029 moles. All right, so if we have that and we then divide that by 0.25, that gives us our 0.1169. So to check that answer, we would have your pH is equal to the pKa, 3.17. So that is your 3.17. Plus the log of the A minus is 0.25 molar divided by the concentration of HF, which is your 0.1169 molar. So when we do that, 3.17 plus the log of 0.25 divided by 0.1169, and that gives us a 3.50, which is the pH that we wanted. All right, and so that is a very difficult problem when you are solving for your either one, your A minus or your HA. But that is how you solve for your HA in that problem. All right, the next one is titrations. So we're starting the titrations, 16.86. All right, so in our starting titration problem, it says, what is the pH of a solution in which 35 mils of 0.1 molar NaOH is added to 25 mils of 0.1 molar HCl? All right, so in this titration, we have our strong acid plus a strong base. When you have a strong acid, HCl, plus a strong base, NaOH, all right, again, we only have three reactions. It's going to be the Ka reaction, the Kb reaction, or the Kw. The only one that has H plus and OH minus in it is the Kw. And so we have our H2O goes to H plus and OH minus, and our Kw is a constant, 1.0 times 10 to the minus 14. All right. So we need to find our concentrations. So anytime we're doing a titration, the reason why they are always hard is because you're adding a volume to a volume. That is how a titration usually works. So MV is equal to MV. We got to find our new concentration. MV is equal to MV. That's how we find our new concentration. All right, so it says that we had, for our OH minus, 35 mils of 0.1 molar. So 0.10 molar, 35 mils. For the HCl, it said 25 mils of 0.1. So over here we have 0.1 and we have 25 mils. All right, so now we need to know our new molarity now that we've added our 25 to our 35. So 25 mils plus the 35 mils gives us a total of 60 mils. So our volume total is 60 mils. So to get our H plus, we take our 0.1 times 25 and divide by 60. And that is a point, I'll leave all the numbers here, a 0.041, repeating a 6. All right, and when we do our 0.1 times 35 divided by our 60 for the OH minus, we have a 0.058 with a repeating 3. All right, and so for Ka, Kw, Kb, any of these, something on the right, or at the equilibrium point, both things on the right have to be 0. All right, and so the smaller one is going to go to 0, and so this is a 0.0416. So we have to subtract a 0.0416. So we have to subtract a 0.041 repeating a 6. And so we have now a 0.016 repeating. And this is 0, and water is a liquid. All right. And so now we have our concentration of our OH minus. Our concentration of OH minus is a 0.016 repeating. And so we can go to the POH, which is the negative log of our 0.016 repeating. So the negative log of that answer, and that gives us a 1.78. And so that gives us a pH of 12.22, which was the question, what is the pH when you do that titration, when you're at that point in that titration. So that is your concentration of your H plus. If you wanted the of your OH minus, negative log of that. If you wanted your concentration of H plus, you just take 10 to the negative 12.22, and that is a 6.0 times 10 to the minus 13. It didn't ask for that concentration, but it may. All right, we will pick up with that one next time. Well, one more thing about this titration, which is a good, easy question to end on anyway. Calculate the pH at the equivalence point. All right, so normally that's a hard question, but when you have your H plus and your OH minus at the equivalence point, that means that these two numbers are the same. Whatever, 0.30, 0.30, pick any two numbers that are the same. It goes to 0, it goes to 0. What you have made is water. So when you have the pH at the equivalence point of a strong acid and a strong base, your pH is equal to 7. The only time the equivalence point pH is 7 is when it's a strong acid and a strong base. If it were a strong acid and a weak base, now you're not producing water. Now you're producing a weak acid. So if this was 0.3 and this is 0.3, that goes to 0, that goes to 0. What you've made is 0.3 molar HA. And so all you can say here is your pH is going to be less than 7. The only one you can give an exact answer for is a strong acid, strong base. If you had your strong base with a weak acid, what that produces is water, which isn't part of our Kb, but it forms an A minus. So you're forming a weak base. So if this is 0.3, this is 0.3, they both go to 0 at the equivalence point, and you make 0.30 molar of your base. So what you can say here is your pH is greater than 7. So we're talking about at equivalence point. So the equivalence point, the two products have to have the exact same concentration. All right, so that's when you have them both going to 0 and you're at the equivalence point. All right, so we will pick up there next time.